The last time Halley's comet swept past Earth in 1986, its nucleus was so dark it reflected less sunlight than a lump of charcoal. Yet that nearly invisible ice and dust fragment has been bright enough in our sky to terrify emperors, inspire astronomers, and rewrite our understanding of how the solar system was built. For most of human history, comets weren't objects in the modern sense. They were omens, intruders in the clockwork of the heavens. The fixed stars stayed put, the planets moved along smooth, predictable paths. But comets arrived suddenly, bright, fuzzy, and undeniably out of place, often sporting tails that stretched across a significant fraction of the sky. Without telescopes or orbital mechanics, ancient observers had to interpret them the way humans interpret most unexpected things, as messages. To a royal court, a new light in the heavens could only mean something about kings and kingdoms. To farmers, it might signal famine or flood, and because comets tend to be most visible near perihelion, their closest approach to the sun, they often show up in historical records clustered around moments of crisis, war, or transition, reinforcing the idea that they were cosmic punctuation marks in human affairs. The first people we know who systematically tracked Halley's comet were Chinese astronomers. As early as 240 BCE, imperial court records describe a broom star, their term for a comet with a sweeping tail, moving against the background of stars over several weeks. These court astronomers weren't doing it for curiosity alone. They were paid to monitor the sky for signs of celestial approval or displeasure. But in the process, they created remarkably precise, dated observations. Centuries later, chroniclers in Babylon, in the Middle East, recorded similarly strange visitors, stars that moved and grew tails. Medieval European monks did the same, copying down appearances with the precision of people who thought salvation might depend on getting the dates right. One of the most famous images of Halley's comet appears in the Bayeux Tapestry, an embroidered chronicle of the Norman conquest of England in 1066. In it, the comet hangs over the scene like a blazing torch in the sky, while King Harold's advisors gesture upward, clearly unsettled. Of course, the comet itself didn't care who sat on England's throne, but by showing up in 1066, it cemented its place in Western historical memory. For nearly 2,000 years, each of these sightings was treated as a separate event, a new comet. The idea that one comet could return again and again required something our ancestors didn't yet have: the concept of gravity as a universal force. That pivot came in the late 17th century with Isaac Newton. Newton realized that the same force that makes apples fall also keeps the moon in orbit and governs the paths of all celestial bodies. His laws of motion and universal gravitation allowed, for the first time, precise calculations of orbits, including those of comets. Edmund Halley, a friend and collaborator of Newton, took those equations and did something quietly revolutionary. He applied them to history. Halley calculated the orbit of a bright comet seen in 1168-2, then dug into older records from 1367 and earlier still, and noticed something remarkable. The shapes of the orbits, their tilt relative to the ecliptic plane, and their timing near the sun all matched closely. What people thought were different comets looked, mathematically, like the same visitor returning on a roughly 76-year cycle. Halley took a risk. Using Newton's gravitational framework, he predicted that this comet, which had appeared in 1168-2, would return around 1758. In an age without space probes, without even the concept of a Kuiper belt or Oort cloud, this was audacious. He was claiming the heavens followed strict, predictable rules. Halley died in 1742, never seeing if he was right. But astronomers after him watched, and in late 175-8, sure enough, the comet returned right on schedule, reaching perihelion, its closest point to the sun, in early March 1759. The prediction's success shocked the scientific world. It was a public demonstration that comets were not one-off divine messages, but members of the solar system obeying the same physics as planets and moons. In Halley's honor, the comet was named after him. The first time a comet was recognized as a periodic returning object. Halley's comet became a physical embodiment of Newtonian gravity, a recurring experimental test of our theories every 3/4 of a century. Each time Halley returned, humanity had new tools to study it. When it passed in 1835, telescopes were better, and astronomers could trace its path with greater precision, confirming tiny deviations caused by gravitational nudges from planets, especially Jupiter and Saturn. When it came back in 1910, Halley reached a kind of celebrity status. Photography had become common, and long exposure plates revealed fine structures in its tail and a faint surrounding envelope of gas called the coma. That 1910 passage also produced one of the stranger episodes in science communication. Spectroscopy, the study of light split into its component colors, had revealed cyanogen, a toxic gas, in comet tails. When scientists announced this, some newspapers sensationalized the idea that as Earth passed through Halley's tail, the planet might be bathed in poison. In reality, the gas was so extremely diffuse that even if every molecule were harmful, it would be far too thin to matter. A typical comet's tail has densities comparable to a very high vacuum on Earth, far fewer particles per cubic centimeter than in the best laboratory vacuum chambers. But the episode demonstrates how Halley sat at the intersection of cutting-edge science and public imagination. By the time of its 1986 return, humanity was ready to do more than simply watch Halley glide by. We wanted to go there. For the first time in history, a fleet of spacecraft from multiple space agencies launched into carefully planned trajectories to intercept a comet. The European Space Agency's Giotto probe was the star of the show, but it wasn't alone. The Soviet Union sent 2 Vega spacecraft, originally designed as Venus probes but redirected after dropping landers on Venus. Japan launched Suisei and Sakigake. NASA, on the other hand, was embroiled in the aftermath of the Challenger disaster and did not send its planned mission, so the primary data came from non-US probes. Hitting a comet is not like flying to a planet. Comets travel on highly elongated, inclined orbits, often with significant velocity relative to Earth. Halley, for example, moves in a retrograde orbit. It travels around the Sun in the opposite direction to the planets. That means that when a spacecraft meets Halley near its perihelion, the relative speed can exceed 68 kilometers per second. At that speed, even a grain of dust has the kinetic energy of a bullet, so the flyby had to be both very fast and very protected. Giotto was essentially a heavily shielded camera on a battering ram trajectory. Until Giotto, many astronomers still pictured comets as loose, fluffy clusters of ice and dust, big snowballs gradually evaporating. But in March 1986, as Giotto's cameras approached within about 600 kilometers of Halley's nucleus, we saw something far stranger and more specific. The nucleus was a roughly 15-kilometer-long potato-shaped body with a surface as dark as fresh asphalt. Its albedo, the fraction of sunlight it reflects, was only about 4%. That extreme darkness comes from a crust coated in complex organic compounds and carbon-rich dust. Beneath that crust, however, the comet is rich in ices, primarily water ice, but also carbon dioxide, carbon monoxide, methane and ammonia. In other words, Halley is not a glowing snowball. It is a black, frozen, volatile-rich relic wrapped in a dirty shell. As it approaches the sun, parts of that shell heat up enough to cause the subsurface ices to sublimate, to turn directly from solid to gas. But this doesn't happen evenly across the surface. Instead, gas escapes through localized vents or fissures, producing narrow jets that erupt from the nucleus into space. The gas drags dust grains with it, forming the bright coma, the fuzzy atmosphere of the comet, and eventually the famous tail, G.